We're now going to look at parametric equations, learn what they are, draw parametric curves given an equation, and convert a parametric equation into a Cartesian equation. So we're used to equations in Cartesian form, generally with y as a function of x. Parametric equations are where we express x and y by using some other variable, what we call a parameter. Usually we use the letter t, so we get y as a function of t and x as a function of t. It's often more useful to define equations in parametric form, and it enables us to graph some more complex functions. Have a go at some. Make out a table with t values ranging from -3 to 3. Put them at every integer, so just put the integer t values along the top, and then underneath a row for x and a row for y, where the x value is t squared and the y value is 2t, and then plot the 7 coordinates you end up with and plot the curve. Then do the same sort of process for this parametric graph here, where you've got x equals sine t and y equals sine 2t, and do this one between 0 and 2 pi, plotting at increments of 1/6 of pi. Okay, let's have a look at the results. Hopefully this is what you achieved. So for the first one and then for the second one. And you can see quite interesting results, particularly this one for the ones with sine t and sine 2t. We can plot parametric equations directly using the calculator without needing to change them into Cartesian equations. And we do this using the parametric equation mode. So we enter the graph mode, we press F3 for graph type, and then if we press F3 again it says PARM, short for parametric, and instead of y equals we then get xt1 equals and yt1 equals, and we enter our equation in there in terms of t using the same button as we use for x. In this mode it will automatically go to t. It's sometimes useful to eliminate the parameter, and we do this by rearranging the equations. Usually if there's a linear one we'll use a substitution for x or y for the t. So subbing the t. Okay, let's have a go at sketching this curve. So we've got x equals 2 cos theta and y equals 3 sine theta. What we're going to do is we're going to think about some key values here. We're going to think about the maximum possible value that x can be, the minimum possible value of x, what x can be, and where it occurs. And do the same for y. And by doing this, we get this result. We know that the most cos theta can be is 1 and the least is -1. So we know that x must be between -2 and 2. And similarly for y, we know that it must be between -3 and 3. If we look at the 4 key values where we get these maximum and minimums, well, the maximum for cos theta will be where theta is 0, and where theta is 0 then y will equal 0, won't it? So x will be 2 and y will be 0. We can continue this process for all these 4 key values. So pick out significant values. When theta equals 0, we get the point 20. When theta equals 90, we get the point 0, 3. Because we would have 3 for y, wouldn't we? And cos 90 is 0, so x would be 0. Think about what happens to cos and sine theta as theta increases from 0 to 90. And that should give you a general idea of the shape of the curve between here and here. And we end up with a curve that looks a bit like that. This basic shape is then repeated, so we can use symmetry to complete the diagram. Okay, so here's some general equations. And this gives a circle, radius r, centre the origin. These equations with t's tend to give us a parabola passing through the origin with the x-axis as an axis of symmetry, and we had a look at one of these, didn't we, in the previous example. And this form here, where we have different multipliers in front of the cos theta and the sine theta, where a doesn't equal b, gives us an ellipse, and this gives us the points it passes through. To convert the ellipse into Cartesian form, we need to use a trig identity. We know that cos squared theta plus sine squared theta equals 1. So, well, if cos squared theta is replaced with x over a all squared, and sine squared theta replaced with y over b all squared, we can see we end up with this Cartesian form equation in terms of x and y. And this is a general form of equation for an ellipse. Okay, have a go at these yourself. I'll show you the answers in a minute. If you're successful at this, then you're ready for the lesson. Feel free to use a graphical calculator to help you with this. Okay, so the first one, we need to use an identity that brings these two together. Tan squared is y over 2 all squared, rearranging this one and squaring, and sec squared is x over 4 all squared. So there's our equation here. We would generally write it in this form with the x and y terms on the left hand side, and this is a hyperbola, so it's usually in the form x squared over a minus y squared over b equals 1. And if we sketch it, we end up with something that looks a bit like that. And you can see those asymptotes, those diagonal asymptotes there. So eliminating t by substitution, if x is 3t, then t is x over 3. So if we replace this t here with x over 3, we've now got an equation in terms of y and x. Tidy it up a bit, and we get y equals 9 over x, or xy equals 9. This is a rectangular hyperbola, which looks like that. And you can see there why it's called rectangular, because the asymptotes our horizontal and vertical perpendicular lines. Here's some crazy ones. There's plenty of crazy parametric graphs that you can draw. Have a go, experiment with your graphical calculators. A few suggestions underneath.